and we have ignition of NASA's Space Launch System solid rocket motor powering us on our journey to Mars.
Hey, Captain Ziegler here, and that was the business end of the new Space Launch System solid rocket booster produced by Northrop Grumman with the intention of taking a new fleet of NASA astronauts back to the moon. Now, each of those solid rocket boosters, and there's two of them on the rocket, provide 3 million pounds of thrust each, well over 3 million. So that's about the equivalence of the weight of the entire cadet wing if each cadet weighed 900 pounds. Now, today we're talking about rockets and staging, and up on the screen here you can see the lesson objectives, so pause if you want to capture those, but let's move on. Now, getting right into it here, the laws governing how rockets work are Newton's laws. So his third law states that equal and opposite reaction. Now, if you throw propellant out the back, it should provide an equivalent thrust to your rocket. And that force is described by Newton's second law, where the force is equal to the change in momentum over the change in time. And momentum is described as the mass times velocity. Now, if we split this up, do a little algebra here, you can see that you can split it into two terms: the velocity times the change in mass, and the mass times the change in velocity. Now, usually that first term, the change in mass term, goes away because Newton's law doesn't account for something losing mass. So there's some algebraic acrobatics we have to do here to get this to work out. But suffice to say, if we look at just the rocket alone, we can cross out the change in velocity over change in time, since the rocket will be producing thrust out the back at constant velocity. So all we're concerned about is the change in mass, and we call that the mass flow rate, or m dot. You'll see there. M dot is the rate at which propellant is moving through our rocket. Now, V sub E, the second part of that first term, is the exhaust velocity of our rocket. Now, our exhaust velocity is extremely high. You can see, you saw in that first video, how fast that column of flame was shooting out the back. Now, you're going to see that second term, A sub E times PE minus P3. That's just the difference in pressure at which the exhaust exits the rocket. So P sub E is the exit exhaust pressure of our rocket, and P3 is the atmospheric pressure. So if your rocket exhaust is a different pressure than the atmospheric pressure, it's going to provide some force on the atmospheric air, or on the air on the outside. So it's going to give you a little extra, or it's going to take thrust away if your exhaust is a lower pressure. So ideally, the exhaust pressure is exactly equal to ambient pressure when it comes out the back. Now, you'll see that that's equal to m dot C. M dot, again, is your mass flow rate, the rate at which stuff is coming out the back, and C is your effective exhaust velocity. Now, that accounts for the regular velocity of your exhaust and the difference in pressure out the back. Moving on here, discussing some of our rocket nomenclature. Here's a picture out of the book. You'll see where all the exciting things happen is the combustion chamber. That's where the fuel and oxidizer are injected into our rocket and ignited. That greatly increases the pressure and temperature in our combustion chamber. Now, the way these nozzles work is we take that high pressure, high temperature gas, and we accelerate it. So in thermodynamics, you can trade pressure and temperature for velocity. And that velocity coming out the back is what provides us the thrust, according to Newton. So you'll see immediately after the combustion chamber is what we call the converging section of the nozzle. The converging section, similar to putting your thumb over a hose, you reduce the area that allows the exhaust to go through, and it must speed up. So it's going to lower in pressure and temperature and then speed up. The smallest area there is called the throat, and that's where the flow reaches Mach 1. Once the flow reaches Mach 1, there's some strange phenomena that occurs because of shock waves, compression, expansion shocks, Prandtl-Meyer flows. All you aero guys out there are probably loving this right now. After the throat, we call that the diverging section. So the nozzle, the area actually gets bigger, and because of small shock waves, the flow will lower in pressure further and accelerate even more. So by the time it comes out the back, it's going much faster than Mach 1. Now, again, I just explained that how in the converging section, the area is decreasing, the change in area is decreasing, but the velocity goes up. Once we hit supersonic, you can see in our diverging nozzle here, again, the strange phenomena that allows faster velocity even though the area is getting bigger. So counterintuitive to what you might see, but once you achieve Mach 1 with flow, strange things happen here. Now, we discussed how a rocket works. Let's talk about the types, the way that's implemented in some common systems here in real life. Most commonly, you're going to see thermodynamic rockets. And that's your chemical, your standard rockets, liquid, solid, hybrid. Liquid rocket, you see a lot of times on first stages where you have either RP1, which is a rocket form of refined kerosene, and you'll see liquid oxygen. You'll see liquid hydrogen, like that's used on the space shuttle. You'll see liquid methane, which is used with the new Raptor engine and the Blue Origin BE4 engine. Solids, like you saw in the very first video, is usually solid aluminum. It's aluminum powder mixed with an oxidizer, usually ammonium perchlorate, and that's all trapped in a gelatinous binder, usually some kind of rubber, and they pour that liquid mixture into the rocket, and it sets up, and once you ignite it, it just goes. Hybrid's sort of a combination of the two. You might have a solid fuel and you run gaseous or liquid oxidizer over it, and the reaction happening there is how you create your combustion and thrust. Solar thermal, that's just where you capture heat from the sun and use that to heat up a propellant and expand it out the back. Electrothermal, that's where you essentially throw a toaster in the combustion chamber. The toaster provides the heat, and the heat increases the temperature and pressure of your propellant so that you can convert that into velocity. Nuclear thermal, no kidding, have a nuclear reaction going on in your combustion chamber, and the heat provided by that nuclear reaction, obviously it's not a prompt nuclear reaction, otherwise you'd have a big explosion there. It's a sustained, just like a nuclear reactor would produce power, this produces heat, which heats up the propellant, and you can expand that out the back and provide yourself thrust. Electrodynamic rockets. So electrostatic, essentially you ionize, you create a plasma, and you take those ions and accelerate them out the back at extremely fast velocities, and this will provide you with very little thrust, but extremely high efficiency, so very useful on orbit. Electromagnetic, similarly, rather than using a electric potential to provide the thrust, the potential is created by both an electric and a magnetic potential. And getting more exotic, you have your solar sails, which use the force delivered by photons to provide you thrust, for photons from the sun usually. Now this is an important thing to understand here. We're comparing the advantages and disadvantages of a liquid and a solid rocket. Those are usually the best to compare in the sense that they're your first stage launch vehicles. So let's talk about engineering trades you might consider when choosing either a liquid or a solid propellant type thermodynamic rocket. Now the advantages for a liquid rocket are that it has high specific impulse, and we'll get to that in a second. Specific impulse is essentially your gas mileage in a rocket. So you get more bang for your buck in a liquid rocket. The other major advantages of a liquid rocket are that it can throttle and restart. And by throttle, I mean it doesn't have to produce max thrust all the time. You can slow the pumping of your liquid and you'll get less thrust, which is nice because you might want to throttle back for a variety of reasons. The major disadvantages of a liquid rocket are that the turbomachinery and plumbing are quite complex. That's actually what gives you the name rocket science here. And then again, handling liquids in and of themselves can be very difficult, especially if they're cryogenic. You have very cold liquids, and they're not easy to store here. So over to solids, they're simple and they're usually cheap. I mean, solids, once you pour up that compound and you have a solid propellant, it's not too difficult to get that thing going. Once it's going, it's just going about its way at full thrust until the propellant's all burned up. Usually a lot cheaper. You're not dealing with extremely tight tolerances in the turbo machinery, and you don't have to. You essentially just have the solid propellant in a nozzle. Major disadvantages, though, are that it can't be stopped once you've ignited it. You can't throttle it, so you can't dial back the thrust. And you really can't test that exact rocket because once you've poured that solid, you burn it and you go about your business. The other major advantage of a solid type rocket is that you can store it for long term. So, for instance, the U.S. Air Force can throw those down to missile silo, and they can sit down there for years at a time without major maintenance. So, if we need to push the button and launch one of those puppies, they're ready to go. Liquids, on the other hand, you can't do that. If they're cryogenic, they're going to boil off pretty quickly, and the liquid propellants that aren't cryogenic are usually quite toxic and can end up eroding and oxidizing a lot of the plumbing that are used to capture it. Now let's talk about some of the expansion phenomena out the back here. Real quick, you should know this is called ideal expansion. So when you're looking at a rocket and you see that straight column of thrust out the back, you'll know that we've taken that extremely high pressure, high temperature in the combustion chamber, and we've accelerated it so much that the exhaust column out the back is exactly equal to atmospheric pressure. So I'll say that again. You have so much pressure in the combustion chamber, you literally have over 5,000 psi or something like that in the combustion chamber. So you have every square inch has the weight of a Honda Civic on it, and you take that extremely high pressure and you expand it through this giant nozzle so that the pressure and temperature are traded for velocity. Now that pressure has dropped so much that out the back it's exactly equal to the atmosphere. We call that ideal expansion. That means we get the most thrust for a given rocket. Next, we have underexpanded. That means we haven't reduced the pressure enough out the back. So there's still the gas is still quite pressurized, and we could have used more of that pressure to convert into velocity. And you'll see that it looks like the plume expands out the back of the nozzle. You'll see that oftentimes when a rocket is high in the sky and the atmospheric pressure has dropped significantly. So while the expansion is still occurring at the same rate and the same way it would on the ground, the atmospheric pressure is a lot lower, so it looks like it's an unexpanded condition. Finally, we have an overexpanded condition where we have converted too much of that pressure into velocity, and we're losing some thrust due to the velocity vector misalignment and some pressure thrust back up the nozzle. So you'll see this, you'll see those shock diamonds in the flow here, and we're going to cut out a quick second to a video of the new SpaceX Raptor engine test firing. You'll see it start and stop several times, but when it fires up, you can see very clearly there's some shock diamond, oblique shocks in the exhaust where it is very overexpanded at sea level. So we'll cut out for about 45 seconds for you to watch that. Take a close look at those, that shock phenomena. Okay, back to rockets here. We're going to talk now about Konstantin Tsiolkovsky's rocket equation. Now, he derived this thing back in 1897, and we know so because he took very detailed notes. So you can see right there in his notes, hey, today's date is, I think it was December 1897. It could be completely wrong on that one, though, so maybe look that up on your own. But he derived it in 1897, and again, we know it because he took very detailed notes. We can see in there that, hey, today I derived the rocket equation. Oh, by the way, make sure to wish Mom a happy birthday. So he took very detailed notes. You can see that in there. He didn't end up publishing it until 1903, but it's quite fascinating. He talks a lot about the future of space travel, and remember, this is the same year as the Wright brothers' first flight. So some pretty amazing stuff in the field of rocketry going on, just as we're beginning to fly within the atmosphere. Now, when he published this, he made a couple of pretty important claims. He said that space travel is possible, and we haven't even flown in the air yet at this time. He said that you must use a rocket, which makes sense. You don't have any air up there, so you must bring the oxidizer and fuel with you, so you have to use a rocket. Can't use gunpowder. He said that gunpowder wasn't powerful enough to propel your rocket for its weight. He said that liquids would have enough energy, and liquid hydrogen and liquid oxygen would be the best. And in fact, that is correct. Except that you can actually get a little bit more bang for your buck out of liquid fluorine. It's a little bit better oxidizer. And you could also have put little particles of either aluminum or beryllium, one of those extremely reactive metals, in your hydrogen to give you a little bit more bang for your buck. But otherwise, he was spot on that hydrogen oxygen would be the best in terms of fuel efficiency. Now, he took Newton's second equation and applied it to the rocket body itself. And he was able to derive the rocket equation here shown on the screen. You'll see that it's delta V equals C times the natural log of the initial mass divided by the final mass. The initial mass is just the weight of the rocket with all its fuel on board. Now the final mass is just the weight of the rocket after all that propellant is consumed. And C, again, is our effective exhaust velocity. So that accounts for the pressure thrust out the back. And I'm moving down here. In the US, we split that effective exhaust velocity up into what's called the specific impulse, or ISP. Now, ISP and effective exhaust velocity are both measures of your fuel efficiency in a rocket. So specific impulse talks about, how much impulse you get per weight of fuel. And aircraft do a similar thing. You'll hear, for you that are going to be pilots, you'll hear about thrust-specific fuel consumption. So how much thrust do you get per pound of fuel in your aircraft? Similar thing with rockets, except we call that specific impulse. And again, remember back to Newton's equation, if we're talking about momentum, either you throw more stuff out the back or you throw it out faster to get more thrust. And it's usually more efficient, it's always more efficient to throw it out faster. And so we'll see specific impulse, the higher the number, the better here. And we'll see for some of those electric thrusters where you're shooting out ions extremely fast, that the specific impulse will be outrageously large because we can accelerate those ions into to relativistic speeds. Maybe not relativistic, but extremely fast speeds, tens of times faster than what you can get with chemical rockets. And so I'll also take note here that to get your ISP, to convert that to effective exhaust velocity, you're essentially multiplying your ISP by 10. So if you ever seen ISP on a rocket, the actual speed at which the exhaust leaves the rocket is just the ISP times about 10. I mean, G naught is actually 9.81, but pretty close to 10 there. So now we have the rocket equation here, and this is important because we can now relate that the delta V we found in earlier lessons to a rocket mass. So we've been talking purely in delta V terms, but now if we have a certain payload, we can figure out, no kidding, how much fuel that's going to take to complete that maneuver. So we have a quick example here, and I thought I had the build on this one, but I guess we don't. So you can see a rocket with, for instance, 300 seconds of ISP. Yes, ISP is in seconds. It's sort of an odd unit there, but don't think about it too much because it's hard to explain in terms of time there. It's not it's not a meaningful unit. And suppose the structural mass of the rocket, and that's just all the metal, the pumps, all the fixed components within the rocket, is about 1,000 kilograms. Let's also assume that the propellant mass is 10,000 kilograms. So we have a lot of propellant in there. And finally, we have a 250 kilogram payload on top. Now, if we plug that all into the delta V equation, you can see that the ISP is 300 seconds times G naught, which is the acceleration due to gravity, 9.81 meters per second squared, times the natural log. Now that's what the LN button is called in your calculator, natural log, of the initial mass, which is just everything there added up, 1,000, that's our structure mass, plus 10,000, that's our propellant mass, plus 250, don't forget about 250, that's our payload mass. And then the final mass of a rocket is just the initial mass minus the propellant that we've used up burning our rocket. So if we crunch it in a calculator, we find out that we get a delta V of 6,466.4 meters per second. Now again, that's meters per second, so just drag that decimal point 3 places to the left, and you wind up with your delta V in kilometers per second. So keep that in mind there, what your units need to be. Okay, moving on. Let's talk a little bit about staging. It's not a hard transition here from rockets to staging, but there are some key differences we have to discuss here. Now, the big advantages of staging is that it greatly increases your delta V by losing some of that structure mass mid-flight. So if you're not using your thrust to lift a bunch of metal you don't need anymore, you can abandon that over the ocean or have it land back on the pad like SpaceX does, and you get a lot more delta V out of your rocket. Now it's not insignificant. It's pretty big, 5x or more payload mass for the same propellant. So if you take the same rocket and make it a 2-stage rocket, so it's the same propellant, same everything, you can get about 5x times the size of a 5x increase in your mass of payload into space here. And that's just by adding one stage. Now, the typical practical limit here is 3, maybe 4 stages. Usually you might see 3.5, and we say half because it's you might have some small boosters at the start, solid rocket boosters on the bottom, but 3 is about the practical limit. You'll see SpaceX does 2. Even on their heavy, those side boosters would probably be considered part of the first stage as well. So usually 2, 3 is the practical limit here for how much you want to stage. It's you get diminishing returns after that. The big disadvantage here is the added complexity. So you have to separate a stage, which is no small feat. You have to decouple those structural masses there, and you have to do it in a well-timed fashion so that you don't have your first stage hitting your second stage in any way, which is what happened on Colonel Nick Hague's first trip to the ISS. The first stage booster collided with something on the second stage, and so they had to abort the mission there. You also have an additional rocket nozzle, and you have to start it up. So there's a lot of other things to consider when staging, but usually it's worth the added complexity. Now let's walk through a quick example here of how this is done mathematically. So for a 2-stage rocket, a lot of the same players here, but we've separated out a couple things. So we still have an ISP, and I should have mentioned here that we might have an ISP that's different for each stage. So we might have an ISP for stage 1, and we might have an ISP for stage 2. Now we're going to split up that structure mass between stage 1 and stage 2. Now stage 1, that's just the structure mass associated with the first stage, the rocket nozzle, the rocket body, all the pumps, all the tanks for stage 1. And we also have a propellant mass for stage 1 as well, and that's just all the propellant for the first stage of the rocket. And then we have a structure mass for stage 2, and that's that's all the structural mass associated with the second stage of the rocket. And similarly, there's the propellant mass associated with the second stage of the rocket as well. And finally, we have a payload mass sitting at the top of both of those stages. Now, the way this works is your first stage is going to be exclusively firing, for part of your rocket flight here. Now, at some point, we're going to lose that first stage and we're going to start to ignite the second stage. So let's walk through how it's going to work. So the delta V1 here, that's the delta V provided by the first stage of the rocket. Now, that's just the ISP of the first stage. G naught, again, that's at sea level, so that's just normal 9.81. And then you add up everything here. So you add up the structure mass of 1, the structure mass of 2, the propellant mass of stage 1, the propellant mass of stage 2, and the payload mass. All right, so this is the weight of the rocket, or the mass of the rocket, just sitting on the pad there. Now, the final mass of the first stage is just the initial mass, the top part of that equation, and then subtract out the propellant because we burned through all the propellant. Now, between the first stage and the second stage, we are losing the structure mass for stage 1. So we're ditching that over the ocean or sending it back to the launch site. So delta V2 here is the final mass from the first stage minus the structural mass, the first stage structure mass. The final mass for our stage 2 here is just the initial mass at stage 2 minus all the propellant we used for stage 2 here. And that is it for the rockets and staging video. Thanks for tuning in. We'll see you next time.
Exit. Stage left even. Having some Murgatroyd. We're going to talk about staging. I believe that is Old Felix the Cat. If you haven't watched those cartoons, your childhood is mostly complete, but you still need to watch those cartoons. Very old reruns. I dare you to YouTube those, but exit stage left, staging. Staging is the tie-in from that very random culture reference to this homework. We're going to talk about what's the most efficient way to get payload into space, which, as you guys know, is already an inefficient process. It's really inefficient. So really, we're just trying to do damage control. How big is the smallest huge rocket that I'd have to build? I'd like to build a small rocket, but a small rocket won't do it. So how small is the smallest huge rocket I could build to get something to space? This is the question, right? Until we develop anti-gravity, we're going to have to do this homework. So if any of you guys have ideas for anti-gravity, please submit them to the Astro Department, because you wouldn't have to do this homework anymore. We could just magically, essentially, send stuff to space. So think about it. But until then, let's do number 2 here. First question asks about 2 advantages, disadvantages of staging. Instructor will go over that with you in EI, or you should have also gotten the sense of why it's a good thing to stage and why it's a bad thing to stage in the conceptual part of the lecture. So let's go ahead and jump to the math as we do. This is the homework from last year, and it says the following. Given a 2-stage rocket with the following characteristics, calculate the delta V total that the launch vehicle produces when carrying a pretty big payload to space, 4,500 kilogram payload to space. And it gives us some stats. It says, okay, the first stage is this big, just the frame of it, right? The metal tube is that big. The propellant we stuffed it with, liquid or solid, doesn't matter. It doesn't matter to our problem here. It does matter in real life, but the amount of fuel it's stuffed with is that much fuel. That's a lot of fuel. And then the ISP, like the efficiency, the bang for the buck of that particular stage and its rocket is 175. The second stage is much smaller. Look how much smaller the structure is. It's a tenth of the size of the first stage. And the propellant is also much, much, much less. And this is common, right? You have a more efficient, right, a higher ISP, 375 versus 175, a higher ISP, much smaller booster to finish up what the original booster could not do. So often what you'll have, this is real life versus Astro 310. In real life, you may have up to 3 stages. You may have a first stage, a second stage, a liquid apogee engine. You may have, but what's real common is you have a single first stage that gets you really high up in the atmosphere. The second stage will kick you out to your final orbit, or at least get you into a transfer orbit, and the liquid apogee engine can do the rest. So anyway, there's a bunch of different ways you could do this. For our problem, let's see if I can not draw the worst rocket ever made. Oh boy. Let's say this is the first stage. I'm really not okay with this tilty line. I have to do it better. Draw it straight across. What I'm trying to do is draw a stage, and then attached to that stage is the second stage. And then up here is our satellite. Now it's usually all folded up like a transformer. It's all boxed up, and then it unfolds itself like a butterfly often. But either way, either it has a third stage or it has its own liquid apogee engine. Either way, what we're saying here, and that's real life again. The problem doesn't say that. The problem says, look, man, the second stage is going to get you all the way out to where you need to go. So the satellite doesn't have its own apogee engine, and there's not a third stage. Stage 1, stage 2, that's all we're dealing with. Cool. Well, all right. We use, like, where you make your money with this is the ideal rocket equation. And that's on the front page of your equation sheet, kind of down near the bottom right, next to home and transfers. Remember life back when we were just doing home and transfers? Life was so good. Well, life is still good, but we're going to use the ideal rocket equation to say how much rocket oomph do we need for each stage, brother? How much rocket oomph do we need for each stage to get our huge satellite? That's a solid satellite out to space. All right, that's pretty tough, but it's doable, and we do it all the time. Okay, so having said that, delta V total that we're asked is, okay, between stage 1 and stage 2, if we mush them together as we have in this one big rocket, rocket noises, rocket sounds. Okay. Between stage 1 and stage 2, what's their total delta V when combined to finally get this satellite, this huge satellite, up to its, oomphed up to its final orbit? That's the holy grail. That's what we want to know. Delta V total for this is just delta V of stage 1, obviously, plus delta V of stage 2. It is that simple. What's not as simple is the delta V of each stage. So here's where we make our money. Delta V of the first stage. Well, the first stage is a rocket. Obviously, it's a booster. And what we want to do with that is plug in the ideal rocket equation. So the efficiency of it, the bang for the buck of it, ISP, times G naught, which we're going to use. G naught is always going to be, in our problems, for Astros, 9.8 meters per second squared Earth gravity, basically, right? Times the natural log, or ln, as I always say, of the initial mass of the stage for the final mass of the stage. Well, what's that talking about? Well, what this is really mentioning is, okay, here we are standing on the ground, and well, here we are. Let's assume we're on the ground. And we have a helmet on for safety. We push the big red button that launches our rocket, and stage 1 ignites. When stage 1 ignites, the booster starts to lift off. It's burning through all this fuel. And what we're basically saying is the initial mass when it's sitting on the ground is everything. It's the mass of the structure of stage 1 plus the propellant of stage 1 plus the mass of stage 2 plus propellant of stage 2 plus the mass of the satellite or the payload of this rocket. This is what trips people up all the time. Forget to actually include the thing that we're launching to space. How dare we? How dare we? That's so rude. But, okay, the ISP, the bang for the buck of the first stage, 175, we measure that in seconds, weirdly, but it's just how we do it. Times Earth gravity, 9.8 meters per second squared, times the natural log of, here's where we make our money. Okay. The mass of everything sitting on the launch pad is, oh boy, I'm just going to start up here, 23,160 plus 254, 250 plus, I'll write it down here, 23, 25 plus 18.8 plus the payload, which is the satellite itself, 4,500. Whew. That is mass initial. That's what we start off with, because that's what's sitting on the pad. Now, after we push the big red button and we burn through all this fuel, the mass of stage 1 after it's lost all its fuel is this huge quantity up top minus the propellant, right? So the structure is still attached. The fuel is all gone. Stage 2 is still attached. Stage 2's propellant is still attached. And of course the satellite, you hope, is still attached. So when we plug and chug, let's see what this gives us. You have to be really fastidious and careful with your values here. So just up top I get 303035 just for funsies. And when I subtract off the propellant that we burned, on the bottom will be 48,785. Okay, cool. So now 175 times 9.8 times natural log 303.435 divided by 48,785. Cool. Gives us 3132.32 meters per second of delta V. Now you guys might be saying to yourself, well, I thought we did delta V in kilometers per second. And we do. That ends up being 3.3, but 3.132 kilometers per second. Awesome. Now, let's do the same thing for stage 2, but we're going to tell the next part of the story. So delta V for stage 2 is also ISP times G naught times the natural log of M initial over M final. Draw a little dotted line here because the story has changed by the time we get to stage 2. First of all, our ISP is much higher. We have a much more efficient rocket here, evidently, in this scenario. G naught is always going to be the same. It's a constant, 9.8 meters per second squared. Natural log of, okay, M initial. By the time we've gotten to stage 2, stage 1 has not only burned up all its fuel, but it has fallen away. That's sort of the point of staging. You let go of all the mass, right, from stage 1. So really, M initial for stage 2 is just the mass of stage 2 and the propellant of stage 2 plus the satellite. So here we go, structure of stage 2, propellant of stage 2, and of course the satellite, we hope, is still attached. Now after the ground controllers push the second big red button that burns the second stage, we're going to lose all our propellant and we'll still have the structure of stage 2 attached, plus the satellite itself. Now in real life, we detach the second stage, usually, from the satellite. For your purposes of your calculations here in Astro 310, just assume the structure of the second stage stays attached forever. Again, not real life, but it does give us the numbers that we need for Astro 310. So no sweat. 2, 3, 2, 5, 8, 8, 0. Nice. Okay, so up top I got 25, 6, 25. On the bottom I got 68, 25. So if we plug and chug overall, gives us 4861.937. Again, this equation spits out meters per second. I'm just going to convert that to kilometers per second, because that's how I do. That's how we've been using it this whole time. So that means that delta V total is the world's simplest addition problem, and you guys can absolutely do that in your sleep. 132 kilometers per second plus 4.862 kilometers per second. Oof, I get that almost exactly equal to 8 kilometers per second, 7.994-ish kilometers per second. If you guys didn't carry rounding errors like I did, you might get almost 8. So, boom, between stage 1 and stage 2, after stage 2 burns through its fuel and then detaches, gets that satellite to orbit if it has at least 8 kilometers per second worth of boost in it. Ta-da! We did it. We launched our huge fat satellite to orbit. So, nicely done. We'll see you guys next time.